Right now, as you watch this video, the universe is playing a trick on us. In 2024, scientists made a discovery that could rewrite everything we thought we knew about reality. Dark energy, the mysterious force that makes up 68% of everything that exists, might be dying, weakening, changing. And if this is true, our entire cosmic address might be wrong. The ground beneath your feet, the galaxy spinning around you, even the distant light from the edge of the observable universe, all of it might exist in a place far stranger than we ever imagined. This is the Hubble Crisis, and it's about to get wild. In April 2024, over 900 scientists released findings from DESI, the Dark Energy Spectroscopic Instrument. This massive telescope in Arizona has 5,000 robotic eyes staring into deep space every night. And what they found has cosmologists losing sleep. The data suggests that dark energy, this invisible force accelerating the universe's expansion, isn't constant. It's changing, getting weaker. Over the past 11 billion years of cosmic history, this fundamental force appears to have been slowly fading away. Here's why this is mind-blowing. Our entire Standard Model of Cosmology treats dark energy as a cosmological constant. The word constant means it should be the same everywhere, always, forever. Einstein introduced this concept over a century ago. It's been the bedrock of physics for decades, until now. But the Desi findings are just one piece of a much larger cosmic puzzle that's been driving astrophysicists crazy. It's called the Hubble Tension, and it's the biggest crisis in cosmology right now. Here's the problem. We have two completely different ways to measure how fast the universe is expanding, and they give us two completely different answers. Method 1. We look at the cosmic microwave background, the ancient light from when the universe was just 380,000 years old. From this, we calculate the expansion rate should be about 67 to 68 kilometers per second per megaparsec. Method 2. We measure distances to nearby galaxies using supernovae and special stars called Cepheid variables. These local measurements give us around 73 kilometers per second per megaparsec. That's a 10% difference. In cosmology, that's not a rounding error, that's a crisis. Nobel laureate Adam Rees, who discovered the accelerating universe in 1998, said the discrepancy suggests our understanding of the universe may be incomplete. In January 2025, his team published their largest analysis using the James Webb Space Telescope, and the tension only got worse. Webb confirmed Hubble's measurements were accurate. This isn't a measurement mistake. The Hubble tension has officially become the Hubble Crisis. So what could explain this? Buckle up, because one leading theory is genuinely mind-bending. There's growing evidence that our entire cosmic neighborhood, the Milky Way, our local group, even the massive Laniakea supercluster containing 100,000 galaxies, all sits inside an enormous cosmic underdensity, a supervoid. It's called the KBC Void, and it's roughly 2 billion light-years across. The matter density inside is about 20% lower than the cosmic average. On cosmic scales, that's huge. And if we're near the center of this giant underdense region, it creates a gravitational effect that makes the universe appear to be expanding faster than it actually is, at least from our perspective. Think of it this way. Galaxies inside the void experience gravitational pull outward, toward denser regions beyond the void's edge. This creates extra motion on top of cosmic expansion itself. When we measure how fast distant galaxies are moving, we're seeing both cosmic expansion and this outflow from the void. This inflates our measurement of the Hubble constant. Cosmologist Indranil Banik calculated that the KBC void could account for an 11% increase in the locally measured expansion rate. That's almost exactly the size of the Hubble tension. But here's the truly strange part. If the KBC void exists, and there's compelling evidence it does, then it creates a massive problem for our cosmological model. Lambda cold dark matter theory predicts how dense any given region should be based on fluctuations in the cosmic microwave background. When scientists ran the numbers, they found a void this large and underdense represents a 6 sigma tension. In statistics, that means this really shouldn't exist. To form naturally within our current model, would require an extremely rare deviation in the early universe's density. Some researchers propose the void might only be explainable if we modify our understanding of gravity itself. Others argue we need better data. Recent studies suggest the void might be significantly smaller than originally thought. The debate is ongoing, and nobody knows who's right yet. But there's more cosmic weirdness at the edge of the universe. When James Webb Space Telescope began operations in 2022, astronomers expected small, primitive galaxies in the early universe. Instead, JWST found massive, mature galaxies just 300 to 700 million years after the Big Bang. Far too massive, far too quickly. Some galaxies measured over 10 billion times the mass of our Sun. Headlines screamed that cosmology was broken. Then in 2024, the plot thickened. Further analysis revealed many weren't quite what they seemed. They contained supermassive black holes actively feeding, creating extra light that made galaxies appear more massive than they were. When scientists accounted for this, many galaxies shrank to sizes fitting our models. However, not all of them did. In November 2024, researchers identified 3 red monsters, ultra-massive galaxies from the first billion years, genuinely as massive as the Milky Way. They formed stars nearly twice as efficiently as expected. These galaxies don't break the Standard Model, but they bend it. They tell us star formation in the early universe was far more efficient than we thought possible. We still have fundamental gaps in understanding how galaxies form. Let's circle back to Desi, because this is where everything comes together. In March 2025, Desi released their 3-year results, nearly 15 million galaxies spanning 11 billion years of cosmic history. The evidence for evolving dark energy got stronger. The pattern held. Dark energy appears to have been weakening over billions of years, becoming less pushy. Let me be clear about what this means. Dark energy makes up 68% of everything that exists. It's the dominant force shaping the cosmos, and we're seeing evidence it's fundamentally different from what we've assumed for 25 years. If dark energy is truly evolving, it opens possibilities previously off the table. Maybe it will continue weakening until gravity halts cosmic expansion, causing a big crunch. Maybe it will strengthen instead, leading to a big rip where atoms get torn apart. Or maybe something completely unexpected. This would require new physics, perhaps a new particle, perhaps modifications to Einstein's gravity, perhaps something we haven't imagined yet. Professor Carlos Frank said it best. If Desi's hints are right, our earlier understanding goes out the window, and we essentially have to start from scratch, revising our understanding of basic physics, the Big Bang itself, and the universe's long-range forecast. Let me tie this together. We're potentially witnessing the biggest revolution in cosmology since discovering the accelerating universe in 1998. We have the Hubble Tension, 2 methods giving different expansion rates, confirmed by both Hubble and Webb. We might be living inside a 2 billion light-year supervoid, skewing our measurements, but that void itself challenges our model. We're finding early galaxies that grew too big too fast. And we have mounting evidence that dark energy isn't constant but evolving. These aren't isolated anomalies. They're symptoms of the same issue. Our standard model of cosmology is incomplete. Something important is missing. What's fascinating is we're living through this in real time. Desi continues observing through 2026. The Euclid Space Telescope is creating the most detailed 3D map of dark matter and dark energy ever. The Nancy Grace Roman Space Telescope will launch soon with even more powerful instruments. Within the next few years, we'll know whether dark energy is truly changing. We'll have better constraints on the KBC Void. We'll understand early galaxy formation in unprecedented detail. Here's what keeps me up at night. What if we're fundamentally wrong? Not wrong that physics doesn't work, clearly it does, but wrong about our assumptions regarding the universe's large-scale structure and evolution. The cosmological principle that the universe is uniform on large scales is foundational to modern cosmology. But the KBC Void challenges that. Maybe the universe isn't as uniform as we thought. Or maybe the universe is far stranger than our current physics allows. Maybe dark energy is connected to quantum gravity in ways we don't understand. Maybe it's a window into extra dimensions. Maybe it's something that would sound like science fiction now, but will be obvious to physicists a century from now. The edge of the universe isn't just a place, it's the edge of human knowledge. Standing at that edge with our most powerful instruments, we're seeing hints that mysteries await we never anticipated. This is the most exciting time to be alive if you love cosmology. We're not just discovering new things, we're discovering that we don't know what we thought we knew. And that's when real breakthroughs happen. The universe is 13.8 billion years old, 93 billion light years across, and contains 2 trillion galaxies. Somehow, in this fleeting cosmic moment, we've developed technology to ask meaningful questions about its fate. Something strange is happening at the edge of the universe, and for the first time in human history, we might actually be on the verge of understanding what it is. The next few years are going to be absolutely wild. Stay curious, keep watching the skies, because the answers are coming, and they might change everything.